Welcome to the STEM Explorer Middle School Introduction to Engineering and Computer-Aided Design Project, or CAD. We are so excited that you've decided to join us on one of our favorite projects. I'm Nathan Elder, STEM Explorer Coordinator at Delta College. Delta College is one of the nation's top community colleges. And since 2016, the STEM Explorer program has worked with tens of thousands of students, teachers, and community members. We're not only interested in advancing STEM in education, but we're also interested in advancing STEM careers. Because right here in the Great Lakes Bay region, in our neck of the woods, we have a lot of STEM-related careers available. And one of those is in computer-aided design. At Delta College, you can get a certificate in computer-aided design in about a year of classes. And most of our students, within a year of starting their program, are already out with a job lined up for them right away. Or you might be interested in taking that one step further and becoming a full-fledged engineer. Well, you can do that. And you don't have to start at a 4-year school in order to do it. You can save a little bit of money and start at Delta College. We have a pre-engineering program. And after those 2 years, you can go on and get a job, or you can continue and get a bachelor's degree by transferring to a university. It's a great way to start. We have a lot of options at Delta College, and that's one of the things that makes us the premier college for STEM. So this particular project is designed to give you a taste of what it's like to become an engineer. And you're going to be doing engineering in this project. So the question is, what is engineering? Engineering can pretty much be boiled down into two things. Either designing a solution to a current problem. We think back to the early 1900s, where there was a need for better transportation, for instance. So they engineered a car. Or improving upon something that has already been designed. So just think about that for a second. Engineering took us from, in about 100 years, this type of race car to this type of race car. This is a 2021 Ford GT. Think about communications. Engineering took us from this form of communication. I bet most of you have never even seen something like that. One of the early telephones. To this form of communication. Quite dramatically different. Big improvements. Now, of course, it didn't happen all of a sudden. It happened in increments. So what engineers do is they work within what's called the engineering cycle. And it usually starts with asking a question. What is the problem? Well, for instance, the problem I mentioned a minute ago is the transportation issue. They needed better transportation, so they developed the car. Well, they imagined, what are some solutions to this problem? And once you do that, you can start planning by coming up with a list of materials that you would need to solve your problem, making sketches and diagrams. There's a lot of ways you can plan. And then you put those plans into action. Usually it involves creating something. Follow the plan and test it out to see how well that plan actually accomplishes what you're trying to accomplish. And then you have to ask questions about what worked, what didn't work, and make improvements. And that usually leads you right around to imagining again what are some solutions for those improvements. Here on the STEM Explorer, we've done a lot of engineering over the last few years, and one of our favorite projects was designing the STEM Explorer arcade. We designed this, I'll show you it, for people who are really into old school video games, ranging from the late 70s to like the mid 2000s. We followed the engineering cycle. We started with the problem. We wanted an arcade machine on the STEM Explorer. And we like old school video games, so that was certainly helpful. And then we started making some drawings, and then we decided what materials that we were going to need, and eventually we programmed this in a program called SolidWorks, and we 3D printed it. You can see all the internal components. There are a lot of internal components in there that we had to order. It's all 3D printed in one piece. It has a HDMI screen, and it works. You can play games on it. We took this and tested it with thousands of students over the course of a whole year. And we listened very carefully to what the students had to say about this prototype. And as they were playing it, we watched them and we tried to find out what kinds of things were difficult for them or what kinds of things were not working very well, things that we'd like to improve upon. We really listened carefully because we were following the engineering cycle. Once we did that, we were able to come up with a plan for a second prototype to improve upon the first one. So I'll show you what the second one looks like. Are you ready? Drum roll, please. Here is the second prototype. You're going to notice it's considerably larger than the first one. There are a lot of improvements in the second one. I'll just go through some of them. The second prototype is 3D printed a little bit differently than the first one. This one is in, I believe, 5 or 6 different pieces. So the original one was printed all in one piece, which made it really difficult to get inside and work on all the internal components because you had to do it with it all pre-built. So you had to be able to get your hands in there. With this one, all these pieces come off. Top piece comes off, side pieces come off, the front piece is one piece, and the bottom is a separate piece too. And it even has some things in here that the other one didn't have, some platforms and whatnot, vertical and horizontal platforms for mounting some of the components. So that's definitely an improvement from a design standpoint. The screen is much larger and it's much brighter. And one of the most important things is you can view it from a greater angle. With the other one, you had to be like right in front of it to see it. With this one, you can view the screen from many different angles and it still looks fantastic, like modern day TVs. This new prototype has more buttons. Includes analog sticks for making or for playing games that are more modern. These are analog sticks, quite a bit different than the digital joystick that's on the other one, and there's a right and a left. You can see a D-pad, which the other one did not have. The buttons for start and select are on the top. There's even a volume control, which the other one did not have. There's a trackpad. That's a little bit different. You can play PC-style games on that one that require like mouse movements and buttons and whatnot. And you'll see that on the side of this, there are 3 buttons on each side. And that gives you much greater flexibility. This one does not have the speaker coming out the bottom, but instead has stereo speakers left and right. So we designed this one based on all the feedback we got from the first one. So we are following the engineering cycle. That was a fun project for the STEM Explorer. Engineering can be a blast. I mean, imagine if you're a creative person, you would really enjoy engineering. All right, so in your project, we're going to start simpler than a video game cabinet, which involves a lot of different kinds of engineering, but we're going to do something simple. You're either going to be doing a chip clip redesign, so designing a better chip clip. You are possibly going to be assigned the task of improving upon the design of a typical salt shaker. Or maybe your teacher will ask you to design a tabletop phone stand. Or a cord management system for a computer desk. We can see the guy there being very frustrated with the massive cords. You may have experienced that. My son recently caught his ankle on a bunch of cords under his computer desk, and his monitor, his $300 monitor, came falling to the floor. Luckily, it was okay. We're going to be using a program called Onshape. You're going to learn how to design, after you've made your sketches, how to actually go into the computer and make these designs online. And then we are going to 3D print your part. You can see this is just an example of what Onshape looks like. We have designed a tissue box cover in Onshape. The project will take you approximately 3 weeks, but then there'll be some time for 3D printing. The STEM Explorer team will have to 3D print all your parts, and how long that takes really depends on how many parts we have to print. So today we're introducing the project to you. The next step will be online tutorials. So my assistant Peter has put together a whole bunch of Onshape tutorials. I believe there are 7 to 10 of those. And once you go through those, you'll have a pretty good idea how to create parts in Onshape. Then you can work on team brainstorming. So depending on the project that your teacher assigns to you, you'll have to talk with a small group of students and work with them to try to come up with an idea for how to make that part better. Then your team will sketch a design on paper, and these can be pretty rough. You don't have to get too detailed, but it helps to actually put pencil to paper before you get into Onshape and trying to design things. Then you'll do the 3D modeling in Onshape for step 5. And here's the cool thing about this. Your team can work on this part at the same time. So let's say you're working on this virtually and you've got 3 students in your team and you're all at home, sitting in your bedroom on your computer or your Chromebooks. You can be working on your part together at the same time or at different times of the day and contributing to it. So it really becomes a collaborative team effort. Then once you're done, you'll submit that part to the STEM Explorer team. You'll actually share that part in Onshape with us. Then it's our job to 3D print those parts. We're actually going to mail those out to your school, and your school will find a way to distribute those parts to you, and you'll be able to test them, and you'll work on a presentation of the results with your team. And hopefully you have accomplished what you are trying to accomplish. But think about this for a second. The engineering cycle is exactly that. It's a cycle. So we were not necessarily satisfied with our first prototype that we made of our arcade cabinet, so we made improvements, and it really never ends. Think about all the cars that we have had and the different iterations of cars over the course of the last 100 years. The cars from the 30s and the 40s and the 50s are all distinctively different from one another, and the cars from 2020 are quite different from the cars even in the 1990s. So at the very end, you're going to vote as a class on what is the best design. And this is important to note. The best design will hinge on a number of factors, actually. The best design is probably one that's not very expensive to make and reproduce, but it's also one that functions the way you want it to function. And your class will vote on the best one, and you'll submit that one to our All-Star Engineers page. And then the All-Star Engineers page will be up on the STEM Explorer website for everybody to see. We'll have a picture of your part and say what school it came from, and you can be proud to present that. So that's the basic rundown of the project, and we want to tell you how happy we are that you have decided to join us on this. We're going to be here to support you for every step of the process. And we are very excited to see what kind of parts that you guys are able to dream up. So best of luck to you. It's great to have you on board this year.